This is Matt Dean with A+ College Ready, and today we're going to talk about uniform circular motion. In uniform circular motion, an object moves in a circle at a constant speed. This might be like a bucket on a string being whirled in a horizontal circle. In uniform circular motion, the direction is constantly changing, even though the actual speed is constant. Even if the speed is constant and the direction is changing, acceleration is taking place. Because remember, acceleration is a vector, and it's a vector that takes into account both an object's speed and its direction. This acceleration is called the centripetal acceleration, and oftentimes we'll abbreviate it as A subscript C. This acceleration is always directed toward the center of the circle. The velocity of the object is always perpendicular to the acceleration. So here we see an object moving around a circle. Let's say it's rotating in a clockwise direction. You'll notice that at every indicated point, the centripetal acceleration is directed toward the center of the circle, and that the velocity is always at a right angle to that. Let's say that this is maybe a ball on a string, and the ball gets to this point and the string breaks. Well, the instantaneous velocity at this point is directly to the left. So if the string were to break at this instant, the ball would move off in a straight line to the left. Since this object is accelerating, there must be a net force acting on the object. And that net force must always act in the direction of the acceleration, which in uniform circular motion is always toward the center. This force, always acting toward the center, is called the centripetal force, and we abbreviate it FC. Centripetal means center seeking, or toward the center. Remember, we said if the centripetal force were to go away, the object would move off in a straight line perpendicular to the direction of the centripetal force at the moment that it disappeared. The magnitude of the centripetal acceleration acting on an object is calculated using the equation AC equals V squared over R. Make sure you realize here that the V is the linear or tangential speed. It's the speed measured in meters per second. We're not talking here about the angular velocity. We're talking about V. The radius is the distance from the center of the rotation to the center of the object. It's measured in meters. Again, remember that the direction of the centripetal acceleration is always toward the center of the circle of rotation. The speed of an object experiencing uniform circular motion can be calculated using this equation. V equals 2 pi r over t. Now again, here we're talking about the linear or tangential velocity, the velocity measured in meters per second. Notice that 2 pi r is going to give us the distance around the circle one time. So that's going to give us the linear distance around the circle, the circumference, 2 pi r. And capital T is the period, the time for one rotation. So this formula is really no different than saying V equals delta x over t. We're taking the linear displacement divided by the time. Remember that the period is the time for one rotation, measured in seconds. The frequency, on the other hand, is the number of cycles, or in this case, the number of rotations per second. Those two quantities, period and frequency, are inversely related to each other. So the period is 1 over the frequency is 1 over the period. So instead of writing V equals 2 pi r over the period, we might also write 2 pi r times the frequency, because frequency is 1 over the period. It's also important to note that an object can experience uniform circular motion and centripetal acceleration without going in an entire circle. It might just complete part of the circle. A good example of this would be a car going around a curve. Typically, a curve is not going to be a whole circle. It's just going to be a part of that circle. Again, centripetal force. When there's an acceleration, there must be a net force. When there's centripetal acceleration, that net force is a centripetal force. It's oriented toward the center of rotation. Here we have Newton's second law, F net equals ma. We've already established that centripetal acceleration is equal to v squared over r. So we can combine these two equations, substitute v squared over r for a, and we end up with this equation for centripetal force. Again, remember that centripetal force is the net force acting on the object, experiencing uniform circular motion, and that it's always directed toward the center of the circle of rotation. But this is the most common equation we're going to use to calculate centripetal force, mv squared over r. Some common examples of centripetal forces might include things like the gravitational force acting on a planet, the force of tension in a rope, if we have a rope attached to something like a ball on a string, and also the force of friction is the force that applies the centripetal force to keep a car on a curve. There are some apparent forces in circular motion. If you're going around a sharp curve in your car, it may feel like there's an object pulling you away from the center of the curvature. That force is a fictitious force. You'll hear some people call that the centrifugal force, which means the center fleeing force. I'm here to tell you that that is not really a force at all. So if you were in this car and you were going around the curve, the force of friction is being applied to the car. So that causes the car to turn toward the center. That force is not acting on you. So you were moving in a straight line. Newton's first law says that an object in motion tends to continue in motion unless acted on by an outside net force. So you continue to move in a straight line until you hit the door. And when you hit the door pulls you toward the center. It feels like you're being pulled outward, but in reality, you're not. In reality, it's your inertia carrying you outward until there's a net force. That force is applied to you toward the center of rotation. So centrifugal force is not a real thing. Also, riders on a roller coaster like a loop-de-loop or a Ferris wheel, it seems to those riders as if their weight changes at different points along the rotation. This is due to a changing value for the normal force between the rider and the seat. If the coaster car or the Ferris wheel car moves at a constant speed, the centripetal force is constant, the speed is constant, but depending on where the rider is, the normal force, or what we might call the apparent weight, is going to change. And we'll see how to calculate those changes in some of our practice problems. This unit also deals with gravity, or the gravitational force. Gravitational forces are attractive forces which act between all objects that have mass. They're field forces. They can act across distance without actual contact between the masses. The weight of an object is the force acting on the object due to its gravity. Of all the fundamental forces, gravitational forces are the weakest, but they do act over the greatest distances. The gravitational force between two objects can be calculated using Newton's universal law of gravitation, which is this equation. So this is the force of gravity, and it's equal to big G, which is the universal gravitation constant. That is constant throughout the universe. The value for big G is 6.67 times 10 to the minus 11 newtons times meters all over kilograms squared. M1 and M2 are the masses of the two objects. R is the distance between the centers of the two objects. Don't necessarily call that the radius. It's the distance between the centers of the two objects. The universal law of gravitation is called an inverse square law because the magnitude of the force varies inversely with the square of the distance between the centers of the two objects. Coulomb's law, which we will talk about in our electricity unit, is also an inverse square law. We also talk in this unit about what's called the gravitational field strength. It's notated with little g. It's essentially identical to the acceleration due to gravity. When we're talking about it in terms of gravitational field strength, it measures the gravitational force per unit of mass at a specific point. The gravitational field strength of Earth is 10 newtons per kilogram. Now remember that a newton is a kilogram times a meter over a second square. So if we divide that by another kilogram, notice that we end up with meters per second square. So this might also be thought of as 10 meters per second square. If you wanted to find the gravitational field strength of acting on an object at a certain point, you're going to take the weight of that object and you're going to set that equal to the gravitational force acting on that object. And we see what we did here. So we're going to set weight equal to gravitational force. Remember that weight is the mass of the object, that's what the O here means, times the acceleration due to gravity. That's equal to the universal gravitation constant times the mass of the object times the mass of the planet, all over r squared. Notice that the masses of the objects are going to cancel out. So we end up with this equation. The gravitational field strength is equal to the universal gravitation constant times the mass of the planet, all over the distance between the centers of the objects squared. We'll also talk about gravitational potential energy. Near the Earth's surface, we can calculate gravitational potential energy using this equation. Gravitational potential energy equals mass times acceleration due to gravity times height. But for objects that are far away from each other in the universe, this is the equation that we want to use, where the gravitational potential energy is equal to the negative big G m1 m2 over r. So as an object moves toward a planet, it loses potential energy. That's how we get the negative sign. And r, we're going to think of as we move toward as a positive value. Some of the potential energy as an object moves toward the planet is converted to kinetic energy. Think of it almost like a meteor or something heading toward Earth. As it moves toward Earth, it's going to accelerate. Its velocity is going to increase. Its kinetic energy increases rather. Therefore, its potential energy must decrease. On the other hand, as an object moves away from a planet, it gains potential energy. So as an object moves away from a planet, we're going to think of r as a negative value. So if we put in r as a negative value, because of this negative sign, the gravitational potential energy is going to increase. So as an object moves away from a planet, its potential energy is going to increase. Its kinetic energy is going to decrease. We also need to talk about gravity's effects on the orbits of planets. Satellites orbit a planet or star because of the gravitational pull of the planet or star. That gravitational force is acting as a centripetal force. The satellite moves in uniform circular motion. Now, we all know that orbits are really elliptical, but we're going to use a circular approximation because it makes the math a whole lot easier. As a satellite gets closer to the planet or star, its speed increases. As it moves away, its speed decreases. The velocity of a satellite can be calculated by setting the equations for centripetal force and gravitational force equal to each other. And we see that right here. Remember that centripetal force is mv squared over r. This ms is the mass of the satellite. We're going to set that equal to gravitational force, which is equal to mass of the satellite times big G times the mass of the planet over r squared. Notice that the masses of the satellite cancel out on each side of the equation. This r can cancel out one of these r's, it can cancel out that square. So we end up, when we solve for v, with this equation. V equals the square root of G times the mass of the planet all over the distance between the center of the planet and the center of the object. So we can think of the speed being proportional to the square root of 1 over the radius. Also, we know that the speed is equal to 2 pi r over t. So if we plug in, if we solve this equation out for t, and we plug it into the equation, we can end up with the period equal 4 pi squared times r cubed all over G times the mass of the planet. So that's a way we could calculate the time it takes for one rotation. And that's it for uniform circular motion. Hope that helped.